Okay. Hello. Okay. Hello, everybody. So welcome to the session on Cyborg. So we'll be giving you a short update on what Cyborg is, why we are doing it, and what we accomplished in the previous cycle, and what we hope to do in the next cycle. I have two co-presenters who kind of stepped aside and asked me to do the speaking. There are a lot of contributors to Cyborg. We'll talk about that. But going forward, what is Cyborg? Cyborg is basically a project for lifecycle management for accelerators. It's aimed at all accelerators available today, including FPGAs, GPUs, various kinds of ASICs, and so on. So we'll talk about the motivation and go into time release stuff after that. So you may have noticed that there are increasingly many kinds of accelerators being used in data centers today, whether in the so-called cloud or in telco space and so on. The reason is that your traditional workloads in data centers were well suited for a general purpose microprocessor. But increasingly, the newer types of workloads, like whether it's machine learning or NFV, are very compute intensive. There is interest in offloading them to accelerators for increased performance and for saving power. So you're seeing this proliferation of GPUs, FPGAs, and various kinds of ASICs, including more coming up this year. We'll talk more about that later in this talk. So the reason we are doing Cyborg is that a traditional way of handling these devices in OpenStack is to define a PCI whitelist. So the PCI whitelist is basically a list of PCI IDs and possibly BDFs which you want to manage. That's turned out to be difficult to use in practice in many cases. But when it comes to programmable devices, it's an additional wrinkle beyond the difficulty of usage, which is that a single PCI ID may correspond to different functions. So we have taken one programmable device, and let's say you put a gzip compression function inside that, and it's got a certain PCI ID. Another card with the same PCI ID could be programmed with a different function, let's say IPsec. So you cannot use the PCI ID to identify what's inside the device anymore. So if you want to say that I want a gzip, you can't locate it by using the PCI ID of the device. Since the device properties are not exposed using PCI IDs, it limits what use cases you can do, such as asking for a device by its function. So what Cyborg does is to discover properties automatically. We do that by installing a driver in every compute node, as we'll see shortly. And that enables us to deliver all the various kinds of use cases. You don't need to set up PCI whitelists or pass-through filters or host aggregates to use Cyborg. And the way we do it is kind of like this. So essentially, we deploy an agent in every node. It's kind of a daemon, and a set of drivers which the operator can enable or disable. And that's going to discover various devices and put them in Cyborg's database, and will report that to placement. So a key idea here is that we are going to model all devices and placement as resource providers, which are nested underneath the compute node resource provider. And the accelerators inside the device would be exposed as resource classes. Okay. So what we got done in this time release is that we actually defined a device model, which we think is fairly comprehensive. It abstracts a notion of a PCI device. We don't assume it's a SRIOV device necessarily. So you could have different kinds of devices. And we implemented our database schema to reflect that. And we also have a few drivers in place. So we can do some device discovery for FPGAs and GPUs. Most of it is already in place as of time release, and the rest of it is kind of taking shape as you go along. So we are able to discover these devices. The agent reports it to the conductor, and we put it in the database as of today. And with version 1 API, you're able to deliver programming. So you can actually program a bitstream in FPGA or do a shell update. We added a glance client for downloading images to do the programming in the first place, etc. We added a GPU driver for NVIDIA, thanks to Lenovo colleagues. And we also enhanced the Intel's FPGA driver based on the OPAE framework. So in addition, we've been going on a parallel track to enable integration with Nova. So the end goal is to be able to spawn VMs with accelerators attached to them. So we created a pilot branch where you put in some Cyborg code where you can test out these different ideas and get reviews. We also propose some patches on the Nova side which are getting reviewed as well. And this code is actually in working condition in the sense that you can actually spawn a VM with the FPGA attached and ask for specific functions. We demonstrated that at the Intel booth the past few days with the genomics-based workload and showed that you could actually offload to the FPGA and get significant speed up and all that stuff. So for train release, we have several things planned. The main thing, of course, is to get alignment with Nova on how we are going to put up a VM with accelerators attached to that. And we want to deliver some specific use cases. So when you're trying to consume an accelerator in a cloud context, you may do it in one of two ways. You could say that just give me that device, I'll manage it myself. So if you know enough things about the device, like whether it's a Tesla P10 or P100 or whatever, or if it's the FPGA ARIA10, you could ask for that and manage it yourself. Or you could just say, here's the algorithm I want to offload, like a gzip or IPsec. Or if it's a telco provider, could say, I want a VRAN to be offloaded, etc. So we cater to both kinds of users with Cyborg. And we also want to add support for more devices and drivers. So in particular, Huawei has announced a new series of AI-related products called Ascend. So there are plans to add drivers for that as well in the course of the train cycle. Okay. If you have any questions, please do stop me. Okay. So what I'll do now is to quickly go through our intended usage model for how Cyborg should be deployed with Nova by the end of train, hopefully. So the idea here is that, like I said before, you're going to install drivers and discover devices to the start of day. And the operator can enable or disable drivers to avoid conflict with the PCI whitelists. So you could potentially have both of them coexisting in the same release. Then you would need to upload Bitstreams. So if you're following a model, if you're not dealing with FPGAs, you can completely skip this step. If you're dealing with FPGAs but in a pre-programmed model, again, you can skip the step. Otherwise, you would have to upload the FPGA Bitstreams or your device firmware images or whatever you want to handle into Glance. And that needs to have the right metadata indicating either what function it's implementing or what device is compatible with, etc. And that could be an error-prone process for the operator to do. So we hope to assist with that by having Cyborg APIs, which would take that bitstream, parse and validate the metadata, make sure everything is right, and then put that in Glance. So it's more like assistance for the operator. The step after that is to define what we call a device profile. It's a newly introduced concept, which is analogous to a flavor for devices. So you would define a flavor for CPUs, memory, etc. Similarly, you would define a device profile like what's shown on the bottom of the screen for devices. Example device profile would say, I want a FPGA with a particular device model with a particular function ID inside it. So as things stand today, we're using IDs, and we hope to move to more readable names in the near future. Any questions so far? Okay. So you would define these device profiles, but where the rubber meets the road is when you set the device profile inside the flavor. So you will go to set it inside the flavor and use that in Nova. But before I go to that, I want to point out that depending on how you define the device profile, we can deliver various kinds of use cases. So in the top one here, we're asking for some very specific region type inside FPGA, and you're saying that I want this bitstream ID along with it. And that's what we call FPGA as a service, because you are getting a blank FPGA and managing it yourself. And the user or the operator needs to know that that bitstream ID is compatible with that region type. So you need to know enough, so it's meant more for power users. If you don't know anything about FPGAs or the GPU model names or whatever, you could ask for something like what's in the bottom. You could say that I want a function ID in a particular device name, and that's it. So it's higher level of abstraction. There's less device knowledge needed on the part of the operator, and we can do that as well. So once you set the device profile in the flavor, you would launch a VM exactly like today. You would ask for a flavor, an image, and whatever else you want, with no additional thing on the command line or on the Nova API. Okay? So any questions on that? Okay. So, yeah. Yeah.
So you guys are still going down the path of embedding the device into the flavor.
Mm-hmm.
So tying device usage to the life cycle of the guest,
Mm-hmm.
rather than providing a service which would let you hot plug devices.
Yep. Hot plugging is of interest as well. So the first phase is setting the device profile inside the flavor. But later, if you're able to decouple that and submit a separate thing, then you could ask for a device profile to be added to a running VM or an existing VM. Yeah. Okay. All right. So I would invite all of you to participate and collaborate with us. So if you're interested in attending our meetings, all the information is here. You're also welcome to contribute to Cyborg. Any other questions? Cool. Okay. That's a very short update. Thank you. Good. 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 Good.